My test watch is okay.
I think mine is right.
Yeah, we have 5 more minutes.
Ashok Maitra Memorial Lectures for year 2017 and 18. This is a annual. We're trying to make it annual lecture. There was initially a gap for a few years, but now it's being held every year. So I request our professor in charge, acting professor in charge, Professor Prabal Chaudhary to. Sorry, it's the first. I request our head of the department, Professor Pradipta Bandyopadhyay, to say a few words about the lecture series.
He did in this department, and but still he was a member of this division for a long time. He was one of our teachers, dean, director, etc., what not, I would say. And of course he was one of the great teachers that this institute ever had, and he was inspiration for many of us in many areas of mathematics: descriptive set theory, probability theory, game theory, ergodic theory, topology, and many others. And this current lecture series is actually originally called ISI Lecture Series in Probability, and this has been renamed as Ashok Maitra Memorial Lectures on Probability Series few years ago. And every year we, as Krishanu has pointed out, we are trying now to make it an annual event. Every year we plan to invite an eminent researcher working in the area of probability and related fields, and the idea is the person will visit all the 3 major centers of ISI, interact with faculty members and students and researchers, of course, give a series of lectures, also have informal interactions outside the lectures. And naturally, some of these will probably lead to some future collaborations and so on. For example, in recent times, we had in 2012-13 we had Professor Offer Zaitouni visiting us. Then 14-15 it was Jean Barthoin, and the next year we didn't have anybody. And 15-16 it was Remco van Hofstad. And last year it was Matthew Penrose, and this year we have Professor Bálint.
And now I Prabal Chaudhary to introduce our speaker for this year.
Thank you. And it's a great honor and pleasure to have Professor Bálint Tóth as our Ashok Maitra Memorial speaker of this year. And to say a few words about Professor Tóth. Professor Tóth obtained his PhD and DSc degree from Hungarian Academy of Sciences, Budapest. So he comes from this old school of mathematics in Hungary. So this institute had many visitors from the school in the past, and one from the same place. He is presently Hale Brown Chair of Probability at the School of Mathematics, University of Bristol, and Scientific Counselor at Alfred Rényi Institute of Mathematics, Hungarian Academy of Science. He has received many awards and honors, and I will not all of them to take away time from his lecture. So a few to mention: he received Young Researcher Prize, Paul Edwards Prize, and the Academic Prize from Hungarian Academy of Sciences. And he is an EPSRC established career research fellow, and he is an invited speaker at the International Congress of Mathematicians in 2018. Now there is something interesting that we know about him. He received Knight's Cross of the Hungarian Republic, which he later returned as a mark of protest. So that says something about him, and I will welcome him again and request him to lead us now.
Thank you very much.
Professor Tóth will give a lecture on Brownian motion and Brownian motion.
Yeah, so
but before that, we have a small two more things. As customary, I'll request our professor in charge to put on this traditional Uttorio.
One before and one after.
And I'll request our head of the department to hand on this memento.
I think it's better to put it with
Yeah.
And pictures are made then.
Yeah.
Thank you very, very much. I'm absolutely moved.
Yeah.
And can you come?
Just open.
It's open. Oh,
Yeah,
okay.
you can open
Okay.
it.
Okay, and it stands like
Yeah.
that. I'm absolutely moved, and thank you very, very much. Indeed. Thank
You're
you.
welcome.
Thank you.
So, on to the lectures.
Yeah.
It's up to you. Whatever you feel comfortable.
We try. We try. Yes, after some time we will forget about it. So, let me thank you very, very much for this invitation. I'm absolutely honored by this, and it's not, of course, some of you or many of you know, it's not my first time at the Indian Statistical Institute, and it's not my first time here in the Kolkata Center. I have been invited to speak in the Jubilee, Platinum Jubilee meeting, which was also a moving gesture from this institute to invite me there, but now I'm indeed very, very much honored. And I enjoyed very much being, this is my last stop. I gave 2 lectures in Delhi, I gave 2 lectures in this series, +1 for the students in Bangalore, and now I'm here and I give this less technical one, and next week 2 more. So it's an absolutely great occasion, and I enjoy doing it. I enjoy collaborating or discussing, maybe it's not yet collaboration, but discussing mathematics with my colleagues. So it's all super. Thank you very much for this invitation. And now let's go to the topics. I hope that Professor Maitra would have appreciated this. He had, as I didn't know him, I just looked up about his personality. He seems to have been a mathematician of very wide range. So that was a characteristic of him, and what you will see here is not a narrow view on a very narrow subject of mathematics, but something broader and sort of embedded in cultural history. So I hope that it fits well to this, to the audience, to the occasion. So you see the title, it's Brownian motion and Brownian motion, and maybe if my message then goes through that, then by the end or by about more than half time through this talk, you will realize which one I mean between quotes and which one I mean without the quotes. So let me say that I will sort of give us a cultural history of what we call today Brownian motion, but also of problems with what we call today Brownian motion. Please come in and sit down. So, as we learn actually I think in high school, this history of Brownian motion, the records we learn and publicly most known starts with a Scottish botanist, Robert Brown, who was a very famous person of his age. He was fellow of the Royal Society later than that, I think, and a very, very distinguished scientist who, as a botanist, and as a progressive botanist who used the modern tools of research, he investigated under strong microscopes at that time, what happens with pollens. So that's exactly it's written there, it's Clarkia pulchella. I don't know exactly what it is because I'm not a botanist myself. But he was investigating the motion of these pollen grains suspended in water, as we all know, this we learn in school, right? And what he noticed was that these things that you see here, which are the pollen objects, which are microscopic, are not that big, this is much magnified, but under the microscope you could observe that these guys move around jitteringly, very, very sort of randomly, as if they had some motor inside, as if they were some alive objects which swim fast or something. There was no explanation to that. It was 1827. There was absolutely no explanation to that, and it was a sort of magical thing. And the microscopes were new. Everything seemed to be new and interesting. So it got popular interest. So it got very, very. So it was an event, a scientific event of the age. People knew about it. There were papers about it, and so this is how we learned the beginnings. But actually, this was not the beginning. This was not the beginning. About 40 years earlier, a Dutch scientist who was, does it right? So he was this universal scientist, also interested in life, in physics, in everything. He was noticing very similar, he made very similar observations as you see with dust coal, with coal dust suspended on alcohol. I have absolutely no idea why he looked at it. So, I don't know. But people, this was the time when the universe at this scale was discovered. So everything measured, everything noticed, observed, described, and he describes exactly the same type of phenomenon. It's not my discovery, so historians of science know about this. But seemingly these observations were didn't have that much impact as the botanists. But it was then, 40 years ago. And if you dig a little bit deeper in history, you will learn.
Was this microscopic?
It was also microscopic, yes. That probably in 40 years the microscopes became much stronger. It was so microscopes. So the optical tools from the 17th century, actually, they were already very good optical tools were created. So I'm not a specialist of this at all. So I will not be able to dig deeper, but there were microscopes. But let me tell you something. We can go deeper, or further deep in the well of time. Namely, back to 60 BC, to Lucretius Carus, who was a naturalist and poet, and describes the Rerum Naturae. That's the big opus, the big work of Lucretius Carus, in which, in verse and in beautiful verse, describes everything, the known universe of the time. And there is one point there where he describes, I will not read it, everybody is able to read in English, this is the English translation of this American gentleman, the British, where he describes in a very poetic way the motion of dust suspended in air and flying around in air. So actually all of us in our childhood had this experiment in a dark room. If there is a slight light coming into the dark room, then in that light you see the dust in that sort of thing. And this is described in poetic terms by Lucretius Carus, which could be interpreted. So if you think a little bit, its motion, we don't know if you are a child and look at it, or if you are Lucretius Carus in 60 BC and look at it, you don't see explanation of it, and it's just poetic and beautiful, and it's very nice what he writes. Okay, so these are the three historical facts. Now let me make a sort of rational reconstruction of what Ingenhousz and Brown at one hand and what Lucretius Carus described. This is today's, looking back without today's knowledge, with all the explanation. So what Ingenhousz and Brown, what they described, these were two different physical phenomena. But we'll come back to this. Is with our today's knowledge, and as they teach us in the high school today, is the following, that the matter consists of, yes, so the fluid has microscopic structure, and the microscopic structure means that there are some, today we call them molecules of the fluid, which float around and move according to the laws of physics, but they are under some thermal motion, which we'll understand later what they are, and they kick around this larger object, which is the pollen. These are the water molecules, or the fluid molecules, which are much smaller scale, and this is a big one, and they kick around this guy, so when they collide, and that's why you see, if you see it under the microscope of that power Brown had at the time, or Ingenhousz had at the time, he didn't see anything of these small guys. He saw the big one, they saw the big one moving around. But today's explanation is that they have these things. Now, what Lucretius did is a different thing. What Lucretius described is a different thing. Lucretius described drifting in a whirly stream of air. So not at this microscopic scale, but there is, in our today's language, it would be turbulent, incompressible flow. Imagine there is some sort of locally turbulent, incompressible flow. There is a suspended object in that which moves along the flow lines, along the lines, the flowing lines. It's not the same thing. So in physical terms, this is on a scale of 10 to the minus 7 meters. So there is a difference of scale of 1,000 between the two phenomena. Nevertheless, the description, if you look from far away, let me just say catchword: scaling limits. So that's why we see the same. Physically, it's a different scale, but in a scaling limit, when you see the abstract mathematical object, it will be very similar. Okay, so this is Lucretius, Ingenhousz, and Brown in historical order. Now let's jump to the beginning of the 20th century. Brown's work was popular. Brown's work was very well known, and people tried to explain. And this was the time when the microscopic structure of matter, that means the molecular structure of matter, there was a debate between wings in physics, who the continuousists and so those who assume microscopic and those who deny the microscopic structure. And in this debate, the Brownian motion became a very important issue. Because Einstein came up in those years, that's the miraculous year of Einstein when he published 3 papers in 3 different topics, and all 3 just determined what happened next century in physics. One is the special theory of relativity, the other one is the emission of photoelectric effect, the photoelectric effect, and the third one is this one about the Brownian motion. And let's go back a little bit in time. In the next slide, you will see what Einstein did actually. But half century before Einstein, Adolf Fick described in mathematical terms. He didn't use these symbols, but described in mathematical terms diffusion, macroscopic diffusion. What happens when you have some concentration in some fluid object, you have some concentration of some material, and that diffuses due to what you didn't know, but the phenomenon of diffusion. And he wrote down this equation in the symbolism of the age, which is what we call today the diffusion equation or the heat equation, as we know. Today we call the same. But let's go back in time 150 years, and more than 150 years, 170 years, and that's a surprise. That's a great thing that it happened. Right? So that means for those of you, I assume everybody who is here can decipher what's in there. Are there non-mathematicians around who don't have anything to do with mathematics? No, then I don't have to describe. So time derivative, time change, rate of changing time of the density of the diffusing material is proportional with some constant which is possibly measurable, physical constant, times the Laplacian applied. So this means that if you have a concentration like that, the Laplacian will push it down, and the density will decrease, push away the density. If you have a negative constant, so a deconcentration like that, then the Laplacian will push it up. So that's what the equation does. It's a very interesting fact of history of science, which I learned when I was preparing this lecture for when I did so the first time, that Fick, this guy Fick, was Einstein's academic great-grandfather. So Fick's PhD student was Einstein's PhD advisor. That's a surprise. That's a surprise. And Einstein came back to this. I don't know whether it had any influence in this sense. So there is but it's interesting. Now what Einstein did was the following. He knew Fick's law, but what he realized that this D how could this D be measured from microscopic effect? I tell you on the next slide what Einstein did in his famous paper. We call it today Einstein-Smoluchowski. On the next slide you will see why Smoluchowski. So there are some physical constants here which I explained. So he derived that D could be determined by temperature. Boltzmann's constant, which was known by that time, so it's a physical constant and it's absolute constant, which is relates Avogadro's number. Anyway, so it's a physical constant which was known at that time, and mu is the following. Think about charged particles, which have a charge, an electric charge, and apply a small field on the observer. Then the charged particles will be moved by the field if the field is very small. So you think about it as a linear effect. So F is small. What is the velocity of motion of the charged particles if you impose a field on them, right? And what he said, so he derived in this paper, I don't have time to describe everything here, but he said that he derived these relations, namely this relation between the diffusion coefficient and the drift. This is what we call today Einstein's relation. Some of you who work in random walk know about Einstein's relation being a big issue to be determined. So this is Einstein's relation, actually correctly called Einstein-Smoluchowski relation. And okay, so that is D in this. And by the way, so what he writes, what is written here is actually the particle, microscopic particle density. Today we would say that this equation is the same as this. Of course it's the same, formally it looks the same, but the meaning is different. In this case, Adolf thought about density of matter being diffused. We didn't have any probability in mind. And in this formula, Einstein, in the same equation, he thought about, or he didn't have very clear probabilistic terms used, but this is what we would call today the density of the distribution of one tagged particle. So what he does in this paper connects the macroscopic diffusion, which is observable under measurable, with microscopic displacement of that particle. So what we call today heat equation, diffusion equation, and a third name it would be the evolution of the density of the diffusion particle. It's not the same thing. Think about it. The diffusion of the bulk or the probability density of one tagged particle. These are two different things. So you need a really big leap of concept to make the link between them. So try to go back 100 years, and today for us it looks like natural. Anyway, and on the other hand, this D here, so if you interpret that way, then D here, which was previously described in macroscopic terms, like really related to the field applied, to the velocity, bulk velocity, and so on, due to this equation is also linked to the variance of the displacement of a tagged particle. So what Einstein did, related the variance of the displacement of a tagged particle with the diffusion coefficient in the macroscopic diffusion. So that's the main point. That's the main point. And in this way it made measurable, it made measure in this way because that's also something observable under the microscope at that time. So it made it measurable. Actually, the point was to determine. I think the point was to determine a precise value of Boltzmann's constant. Okay, so that's Einstein, and here is Smoluchowski. Unfortunately, I didn't find a stamp showing Smoluchowski, but I found a picture of him dancing with his wife. I think it's and it's so beautiful that I couldn't resist putting it. That's indeed Mariusz Smoluchowski. Marian Smoluchowski was a Polish-born Austrian. At that time, Eastern Europe was a mixture of cultures and nations. So he was Polish-born. The Poles say that he was Polish, but he lived in Vienna many years and he spoke all languages. He could shoot spoken. And about the same time, Smoluchowski wrote a paper about exactly the same problem, and what I looked in both papers. These are papers written in German, so I have difficulties reading, but these are translated papers. That mathematically Smoluchowski's paper is more sophisticated than Einstein's paper was. That's a fact. And Smoluchowski has the same type of theory of Brownian motion. Mind, the importance I want to emphasize it again is linking macroscopic diffusion with microscopic jittery motion, right? It's more, for example, the Kolmogorov-Chapman. He realized what today we call Kolmogorov-Chapman or Chapman-Kolmogorov equation is there in Smoluchowski's paper, right? So he discovered, he was forerunning Chapman-Kolmogorov. He didn't think in terms of Markov processes and so on, but he realized what's the important point. It's a very interesting paper. There is actually some scientific, some historic controversy whether Smoluchowski had some priority, but I'm not going to eventually published later, but there are some coincidences why. And another hero of the same time is Jean Perrin. Jean Perrin was a French physicist, and he was also, people, the big names were obsessed, but big people, really big thinkers were obsessed by Brownian motion. So Jean Perrin has this book. Where is the book? Do I see the book? Yes, Les Atomes. So that was published in 1912, and it's a compendium of the physics, atomic physics of the time. Not atomic physics as we think today about atomic structure, but atomic structure of the atoms. It's not about that. It's about atomic structure or microscopic structure of matter. Right? And this drawing, this picture, is from Perrin's book. This is copied from Perrin's book. This is not a random walk with coin tosses and all that. This is the observation of a particle moving under, or an atom or a molecule moving under the thermal agitation of the fluid, noticed by observation. He observed in discrete times, he observed where the particle is, and he made on this sort of paper with grids, he made this. It's a very beautiful thing. Today we will think that this is a Brownian, this is a random walk trajectory. No, it's not a random walk trajectory. And one more name from the same age, actually earlier than this, is Louis Bachelier. Louis Bachelier was not a physicist. The other people mentioned so far were all interested in physics. Louis Bachelier didn't care about physics. He cared about money. Okay, this is too bad to say, you know. He cared about speculation for money. He cared about business. But not because he was a businessman. He was a mathematician. He was a brilliant mathematician. He was a PhD student of Henri Poincaré. He was a PhD student of Henri Poincaré, and under the supervision of Poincaré, he wrote this thesis, which later became a book, which is called Théorie de la spéculation, the theory of speculation, in which he describes what today we call basics of financial mathematics. Okay, not that much sophisticated things as hedging and whatever, but that behind it, of course I would call it Brownian motion, a random object is, and why this is a very subtle and fine mathematical work is that he's the first one, and unlike Smoluchowski and Einstein, who seemingly the traces of thinking about Brownian, okay, what we call today Brownian motion, Wiener process, let me call it Wiener, it was before that, as a stochastic process, not only as a collection of random variables, but about paths. He asks questions about paths, for example, the maximum in an interval. That's not a random variable determined in terms of fixed time behavior. What Einstein and Smoluchowski did is essentially describable in fixed time terms. And what Bachelier did, it cannot be described with given a number of fixed time instants and look what happens then, but only in terms of path. And that's the great thing. It's a very, very fine one. Totally forgotten till the 60s when the big boom in financial came and Bachelier's work was rediscovered. Actually, he had a very unhappy life. So he was in a small place, a professor in a small university. I don't remember now all the details, but he didn't make that big career as the other names mentioned. So, but he got rewarded by history, because today Bachelier is the greatest thing. Okay, now let me make a rational reconstruction of what Bachelier, Einstein, and Smoluchowski did. So again, this is a rational reconstruction. It's not that they spoke about everything in this language. This is how we look back today and our way of thinking today. they defined, putting together these three works, the works of these three people, what they thought about was what we start with when we teach Wiener process in our courses in stochastic processes, namely that we want to understand a stochastic process which in time evolves. It takes values in Rd, in case of Bachellioni in R1, but in case of Einstein and Smoluchowski in Rd. And what characterizes this process, this random motion, is characterized by some very important thing. First of all, I define the increments. The increments mean take non-overlapping time interval, or sequentially take increasing time instants, and the intervals between the time instants is called, so what happens in between is called increment. This is increment in the interval from t0 to t1. This is the increment in the intervals from tk minus 1 to tk, right? These are the increments. Now what we realized is that on a non-overlapping time intervals, the increments are independent. Must be. So that's, okay, let's take as axioms. We didn't use this term, but axiom. That the increments are independent. The increments are stationary in time. That means that it doesn't matter what I put, if I always think about ask about questions about the increments, doesn't matter what I put the beginning of time. Right? So the laws don't change in time. From these two, with our knowledge today, but even with the knowledge of that time, you easily guess that the expectation could be only a constant time t, that let's take that constant 0, that's just so zero expectation, and that the variance of the increment must be proportional with the length of the time of the increment. This follows only from these assumptions, if it's finite, right? So this is, and another thing which was not explicitly said, but it was so natural that it didn't need to be explicitly said, that the path is continuous. Continuous path with these properties, random path with these properties, is what we speak about. Now if you have all these, again a little bit reconstructed, a little bit by today's knowledge, but it could have been done at that time, and actually they knew that from these it actually will follow that the distribution of the increment is Gaussian, normal, Gaussian, with variance proportional to the time interval. So that's what Bachelier, Einstein, and Smoluchowski. So they did a bit more, but this is a summary.
So that was like first decade of last century, like first decade of.
Yeah.
So did they have a notion of independence at that?
Not quite.
Yes.
Not quite. So that's why I say that
so
rational
how
reconstruction.
would they describe?
That's the world of physics and of ideas doesn't develop like that. That's how we teach.
Yeah.
That's
No, how would they say it? I mean, stationarity I can understand.
Uncorrelated. That's the correlate. That uncorrelated, and whatever that means.
Okay.
So there were no clear probabilistic terms. But if you look at Einstein's paper, or if you look at Bachelier's paper, then you see that these things are there, even if not said. So, that's a very important conclusion. The history of science is not rational. The history of science is not. What we see looking backward is rational. Good, let's go on. And it's still Bachelier, it's still that time. It's still that time another physicist, Paul Langevin. This is for the physicists, for those of you who have some physics intuition. For Paul Langevin, so the physicists there is a very important problem to be worried about if you think about motion of a particle. Namely, if you start thinking about all these, you realize very fast that the particle must have infinite velocity. Such a motion can't be a motion with anything like velocity. Always infinite velocity. Infinite velocity which changes always direction. That doesn't make sense. Doesn't make sense. And that's why Paul Langevin invented something else, which we call today backwards looking Orstein-Uhlenbeck process. Namely, instead of what I described before, he thought it slightly differently, saying he thought about this is Newton's equation for the motion of a particle. Acceleration, this is mass. Acceleration of a particle, mass times acceleration is force. The force acting on a particle be equal, I wrote it in one dimension, but it could be in any dimension. It is equal to what? It's equal to minus a negative constant times the speed of motion. If you don't cycle in this country because it's dangerous. But if you cycle in another country where it's not dangerous, then you notice if you try to cycle faster, you feel a stronger force which keeps you back, right? So there is a force which keeps it back. So there is a force which acts linearly, opposite to the motion, linearly in the velocity, plus something mysterious, namely the thermal noise. So these kicking from here and there and there. So this is a force arising, a force which is uncorrelated in time, has zero mean, and it's uncorrelated in time, so the force acting at this time instant and the force acting on that time instant are uncorrelated, which would mean this, again, I use notation which Langevin did not use, but described it. Again, things don't quite make sense because this doesn't make sense as a function, only later we knew that random distribution can be, but this is what we call today the white noise, which is the derivative of what today we call linear process, right? So nothing makes clear sense, but mind that Langevin was an ingenious physicist. He didn't care much about mathematical rigor, and what he describes is what today we call the Einstein-Uhlenbeck process, and we know that it's very, very intimately related to Brownian motion. Let me not go into much detail, but it is intimately related in some limit. From here you get what we call today Wiener process, so it's related. Anyway, it's another hero of the story. These are another hero. And now comes a new era, a third chapter. Question?
So, did the people who had the Fourier knowledge, like Fourier series and everything, Fourier transform, did they see or interact with these people? Because it was natural to solve these equations through Fourier methods.
You will see next. You will see next. I don't know about the old times, about the 19th century. Of course, yes, certainly. So if you look at Fick's, at the old diffusion equation, then it was solved. So there were methods to solve it in Fourier in the 19th century, but it has nothing to do with microscopic, right? In constructing the microscopic picture was not good, right? But there another age came, and this guy here, who is Norbert Wiener, he grew up with Fourier. He was a Fourier analyst. And the big thing he realized, these are all geniuses, needless to say. So Norbert Wiener realized that this is a very deep mathematical problem. This is a very deep mathematical problem that I described the object, what I summarized as a rational reconstruction, which is easy to strike down on a page of paper, this is what I want. And it's very convincing that it's a good object, and the physicists would not care about more, just use it. But realizing that, look, does such an object exist? What is the question? Can we construct a space? We want continuous motion. So on the space of continuous functions on the interval 0, 1, can we define a measure, a probability measure, which gives exactly those properties for the random variables involved? This is a deep and difficult question. And this is what Norbert Wiener realized in 1921-23, and later with Raymond and Paley, and he gave a proof of existence of this object, a very, very difficult one. Mind, there is something which I'm not sure everybody, I speak about the probabilities here, I didn't know time earlier, so 10 years ago. When I'm preparing this talk, not for this, but a similar talk for another occasion, that I learned actually about. So that there was an early paper of Norbert Wiener dated 21, where he makes the construction of Brownian motion absolutely without Fourier transform, using this pure functional analysis, using a generalized notion of integration on function space, which I didn't go into details, but very beautiful thing seems to be, and putting down the axioms. You can see here are the axioms he wants to satisfy, so that's exactly what we want. And in this paper there is no Fourier analysis, it's an abstract functionality construction that on the space of continuous functions C01, as we call it today, you can construct an averaging procedure, that means a measure, which has exactly this. But this was so abstract, people, that it didn't have much impact, and because it was too abstract, probably the functional analysts of the time didn't appreciate that much. And Norbert Wiener and Raymond Paley later, being both Fourier analysts, they realized that there is another way of constructing. And that's what we know best. Namely, the rules of the game are the following. When I say constructing, probabilists who are here know well, and I tell you all, you can use countably many independent coin tosses and nothing more. Or countably many independent standard normal random variables, because the two can be constructed from one another, and nothing more. Not more than countably many. So if somebody tells you, I don't speak to the probabilists now, of course, that take an uncountable collection of independent random variables, then tell that guy that I don't think. There is nothing to it. Okay, in some very abstract world you can construct it, but it's useless. You can't. So the rules of the games are the following. Take countably many independent standard normal random variables and construct the random function only using them. And that's what Wiener and Paley did in their 1933 paper. Now write down everything properly. Write down, take these let the size be the independent random variables. So this is a Fourier series with random coefficients. The Fourier series with C sub k are just deterministic numbers, which are not difficult to determine once I know what I want. The difficulty is that I determine this C sub k. This C sub k will decay like 1 over k. Like 1 over k. So the L2 convergence of the sequence will not be difficult, because when you take the L2 norm, you have sums of 1 over k squares, which converge and no problem. But that's no good, because you want the function. You don't want the L2 element. You want the function. You want continuous function. That's the magic. Continuous function. And you have to prove that this Fourier series actually converges almost surely uniformly. And that's difficult. And that's very difficult. And that's the difficulty of Wiener's construction, or Wiener and Paley's construction. It was done. It's an absolute wonder, an absolute difficulty. Right? And this is the only stamp I found where Brownian motion, okay, what we call today Brownian motion, appears. I didn't find another stamp like that. This is a stamp of the Czechoslovak. So it was a meeting of the Czechoslovak Mathematical Society back in some old, I don't know, I will not find it, sometime in the 60s.
But when was this constructed of Levy, where he uses this only to on Dirichlet rationals and then...
Wait a second.
Ah, okay.
It's coming. It's coming. So there are experts. Of course I knew that there are experts. I just don't know. So this is wonderful, right? But the difficulty is indeed proving this uniform convergence, and orthogonality doesn't happen. You have to group terms, and it's very, very beautiful, but difficult. And here it is. So Paul Levy came about to say slightly, okay, this is in the 30s. He wrote this enormous number of absolutely wonderful papers. And he gave indeed an alternative construction, rather than constructing it using Fourier basis. Better use, I think I would call today Rademacher basis or something, which helps better. Don't use the orthogonal basis, but integrate them. And in plain geometric terms, it's here. Take a Gaussian random, standard Gaussian, and draw a line. That will be the end of, this is time 1. Then take another standard Gaussian, independent of the previous one, and at the half point, put another point, not at the step, this distance, there is some constants coming in at each step, which is easy to compute. And then you have the 2 broken lines, I mean the line broken once. Then do the same thing, sorry, this is the problem. Then do it the same, so at each consecutive times or construction step, you halve the intervals and you use independent Gaussians multiplied with a constant, which is easy homework to compute what the constant should be, and do that what you see in this picture up to the first one.
Basically, multivariate regression of Gaussian. That's
yes,
the formula.
That's true. So if you are a statistician, as I guess, that's what you do. Yeah, yeah. It's a multivariate. It's a regression. what. Now, and that's what Levy did. And proving uniform convergence of these is easier. So when I teach construction of Brownian motion, that's the way. So I mentioned the other one, I give some homeworks from the other one, and then this is the way I teach it because it's true. And I think I'm not even good. And here is the famous book published in 1948 by Paul Levy, in which everything is a Bible. Yeah, and he calls the book, maybe this was the first, I don't know. So yeah, Processus stochastique et mouvement Brownian, which is, but I'm not sure whether Wiener used the Brownian motion term. I'm not sure, no, I will not look for it. I think Wiener already used the term Brownian motion for this terminology. Good, so that's the first historical part of my talk. And here is the conclusion of the first historical part, namely that what Wiener constructed, and we call today Wiener's process, is an absolute goldmine. Everything of mathematics is there. So if you are a functional analyst, whatever you do, somehow you should try and find a model in Brownian motion. If you are a topologist, if you are a real, if you are, indeed it's a goldmine, very much is there, very, very much is there. And not only for pure mathematics, but also for applied mathematics. I just collect the number of things from financial to physics to quantum field theory to everywhere Brownian motion is there. It's absolute goldmine of pure and applied mathematics. Okay, so that's the history of, and maybe I told you, maybe I showed you that this is what I mean between quotes. This is what I mean between quotes, because the true phenomenon is a physical phenomenon. This is a mathematical construction, a wonderful mathematical construction, which gives work for mathematicians, has given work for 100 years, and will keep mathematicians busy for much more, and it's really a great thing. But the true problem is a physical. How is this thing related? Of course, Einstein may give some background, but Einstein's Smolkovsky, but they just sort of guessed. So it's nothing like giving a physical explanation. Just there is a physical description and some axioms derived from the physical description and the mathematical construction. All are great, but you will see next what I miss. Okay, now before going there, let's go now. How is it related to random walk? So the story is older than it didn't start with Brown. It started with Abraham de Moivre, who was a big hero, as you all know, of 18th century. There's very beautiful stories about Abraham de Moivre. And the central, it starts with the central limit theorem. So I want to link now a discrete motion with this continuous thing, right? And Abraham de Moivre was the first one, as we know well, who proved what we call today the central limit theorem, namely that if we add independent steps up and down with probably 1/2, say, then in the long sum limit and scaling properly, this will converge, the distribution will converge to a normal, as you see there. So this is Moivre. And then the random walk problem, I jumped a lot, and probably I missed some big names here, but I can't do everything in this short talk. The next person I want to speak about is Poya György, as we say, or you call it George Poya, who realized in the 20s how interesting an object is a random walk on the lattice. And he wrote this famous paper, and this is a mistake, I just checked it today, but after I sent the PDF to Krishanu, that this was not 23, but 21. Not a big mistake, but better, it's 21. He wrote his famous paper in which he proves recurrence, the duality, or the binary, or how do you call it, so that in one and two dimensions random walk comes back, and in 3-dimensional random walks it doesn't come back with probability 1. And that was a great thing, and it's full of very beautiful mathematics, the paper of Poya. And not everybody knows, in English it doesn't say much, but in German and also in Hungarian, we don't call it random walk. We call it random wandering or random rambling or something like that. And this term, Irrfahrt in German, was coined by Poya in that famous paper. And random walk, I think rambling or random wandering is nicer than random walk. But anyway. And Andrei Kolmogorov is another hero of this story, who, of course, needless to say, so he was the person who realized that stochastic processes in general, of course, beside, I don't want to diminish Paul Lévy's contribution, of course, but Kolmogorov was the one who realized the big thing, that what stochastic processes and why these things are so important. So these are two other heroes, and not only, because this is about, okay, these are random walks. We know for now from actually going from around the Moivre that if you just look at the final position of the random walk at late time, then that will converge to a normal. What happens in between? In between, what happens is Brownian motion. And the heroes I mentioned here are Erdős, Katz, and Donsker. I want to draw your attention to this one in particular. And I tell you, this was there in when I first gave this talk. It's not prepared only for India. Now, this is a mural from an episcopal. It's called Saint Gregory of Nass, I don't know, somewhere in California. There is an Episcopal church built in the 80s or 90s. It was final. The mural was finalized in 2000s, early 2000s. Then the Dancing Saints. It's an absolutely non-conformist mural with what the artist thought about who are saints. And there are about 100 saints dancing around in this particular part. You recognize this person, I guess? You recognize that person? Sorry? Erdős, Paul Erdős. That's Paul Erdős. That's for Paul Erdős. That's Paul Erdős. None of them. Okay, the other one is Martin Luther. I don't know who the last person is. Anyway, this is the type of. Okay, let's go back to. If you want more information about this mural afterwards. So Paul Erdős and Mark Katz are the heroes here. Who realize the following thing, that you can do more than the central limit theorem. You can look at the trajectory of the random walk between 0 and the late time, or project it to the space of continuous functions by shrinking time to 0, 1, and you easily guess shrinking space by square root of n, right? And what they realized, that this function in the function space, if you think about it as an element of the function space, or if you think about the distribution, the probability measure on the space of continuous functions 0, 1, over 0, 1, that measure will converge to something which Wiener constructed, will converge to Wiener's measure. This is a big thing, and lots of information can be taken. It's not just a nice mathematical fact, it's a very deep. And this program board was finalized in the end by Muro Donsker. So it was the Erdős and Katz wrote their paper in 1946. They wrote two big papers on probability together. This was one, and the other one was about the prime number, about the distribution of prime numbers. So it's number 13 papers, probabilistic aspects of number theory. But I don't mention that one. And this is one. Unfortunately, there are no stems either about Erdős or about Mark Katz. There should be. Good. So this is the invariance principle. So we went now from random walk to Brownian to Wiener process. So we know how to go from random walk to Wiener process. We know how to construct Wiener process. We know a lot, but we still don't know what it has to do with physics, right? Now here we come now from Brownian motion to Wiener process, and when you see Brownian motion without the quotes, I mean the physical Brownian motion. That means I have a physical object, I have the particles moving around, I give some initial conditions to the particle, they move around, they kick each other, and so on, I follow one of them. Can I say something about the trajectory of it? Right? And what I want to emphasize here, that mathematical modeling is one thing, and deriving it with mathematical rigor from microscopic principles, something is another thing. Both are interesting. Mathematical modeling is much more easy than deriving. So both are interesting, both are important, but they are way different in difficulty. This is a much more, in this particular case, much more difficult thing, because we know what we want. We know that there are Newton's laws or quantum mechanics, or you can define other laws, and you have to derive something well defined. Now this is the problem. So the problem is, in all cases, and from now on I speak about this, that the successive displacements are not independent. That's an idealization, that the successive displacements are independent. So deriving Wiener process from random walk, mind that in Wiener process one of the main characteristics was that the increments are independent, right? Of course, if the increments of the random walk behind are independent, then you can derive this. It's not easy, but you can derive it. But what happens when in true life the successive displacements are not independent? Because that particle which moves under collision with others has memory, because once this collided with another one, this goes away, collides with the third one, the fifth one that comes back and collides with this one, it has information from the past. Very difficult. And it's not only that the mathematicians want to be pedant, but it's deep, right? And this is the two problems, how to derive tagged particle diffusion. Here is a problem. I put down billiard balls and let them move and collide with each other, infinitely many if you wish, and follow the trajectory of one of them. Initial condition is random, otherwise everything is deterministic. Can you say something? Now this is a very deep and very difficult problem. There are some very important results. I mentioned a set of results which was by Thierry Bodinot and Laure Saint-Raymond in these years, in the last couple of years, where they did something. I will not speak about details of this one because it would take too much techniques and time, and I will speak about other things. Here are some models we want to understand, and one of them is the Lorentz gas. One of them is the Lorentz gas. The Lorentz gas goes back to the same time of the beginning of the 20th century with Hendrik Lorentz and Boltzmann. Namely, you put down scatterers in RD, which may overlap. I didn't let them overlap here, but they may overlap if you wish, which are infinite mass. They're put there and don't move. Right? Say, take a Poisson point process on RD. Poisson point process on RD and put down scatterers of radius r. Now let a particle start with some velocity, some random velocity, velocity of size 1 but of random direction, and move according to the laws of physics with elastic collision. The scatterers don't move. This is a random motion. There are two randomnesses, namely how you put down the scatterers and how you start in which direction you start your particle. Otherwise, it's deterministic. Follow the trajectory till late time. Can you prove a central limit theorem for the displacement? Here is another one. This is the random and what we call the periodic Lorentz gas. Put down periodically these scatterers. And again start with a random velocity, randomly oriented velocity. And let the particle go. It's like a random walk, but not much like. It's like a random walk because it goes from lattice side to lattice side essentially. But the next step is not independent of the previous one. It's a deep deterministic. And there is something we call the Boltzmann-Grad. The Boltzmann-Grad limit here, when you take, I will not describe technically, you take denser, the density of points is larger, but the radii are smaller and much smaller. There is a way of taking it so that the free flight stays of order 1. Right? And that's an interesting thing, the Boltzmann-Grad limit. In the random case, this picture tries somehow to mimic the Boltzmann-Grad limit, and this one in the periodic case. So that means that they are dense, much denser there, but the radii are decreased faster than linearly, and therefore only in times of order 1.
So that means in the Poisson case, the intensity is getting bigger.
The intensity is getting bigger, but okay, let me write down because then it's good that I have in the following way. So rho goes to infinity. R goes to 0 in such a way that rho times R, well, if I put rho times R to the D go to 0, there's no good. There's no good because they're just linear decrease, and then, but take rho times R to D minus 1, stays same 1. This is the Boltzmann-Grad, right? It's more general than that. And so here is the Boltzmann-Grad limit just to explain. Now, if you, the problem itself, so if you take this diffusive scaling without Boltzmann graph, just the problem I defined in the previous slide. So take this one, take this motion, take the density small enough, or the radius small enough, depending on, the density not too high, or the radius sufficiently small, such that you are not trapped with probability, because then there is no question. And then ask about this is enormously difficult, and we don't know the answer. It's a very important, basic important question. In the periodic case, it's still very difficult that there are some answers. So what I say here, that problem is fully open for the random. In the periodic case, there are very deep things done by Sinai and Bunimovic and Chernov. In two dimensions, it is known. In the so-called finite horizon case. The finite horizon case means take a periodic configuration, but not like here, because here you have infinite. You can go to infinity without collision with probability 0, but nevertheless there is a straight line. Finite horizon would be something like this, a periodic configuration. A periodic, so continuing periodically like this, right? You don't have there is no direction where you can go to infinity, where you can draw a ray to infinity. So in the finite horizon case, in the finite horizon case, the invariance principle converges to Wiener processes known. In the infinite horizon case, it's known in 2 dimensions, but open in 3 and more dimensions. By the way, the previous one is also in 3 and more dimensions. There is some conditions which are not checked, but it's mathematically it's slightly. In the infinite horizon case, you have to scale not by square root. It's super difficult. You have to scale. This has number theoretic causes, but it's known. Now, if you randomize the scatterers, that means that you cheat a little. Namely, there are scatterers, but there is some randomness at every scattering. You allow some randomness at every scattering. It's still not independent steps, one after the other one. And I have some old paper. This was one of my first papers I wrote in my life about the limiter. It's an interesting thing. Now, if you do first the Boltzmann-Grad limit, first take the Boltzmann-Grad limit, and then as a second step, try to do a diffusive limit. It's a 2-step limit. First take a Boltzmann-Grad, you will have a flight process. Then, for the flight processor, take a diffusive limit. Then, again, there are results for the Boltzmann-Grad limit is a random Lorentz gas, when Poisson scatterers are in the Boltzmann-Grad limit, which you don't see. There are results by Galavotti and Spohn back in the 60s, 70s, in 2 steps. If you do it in 2 steps, I emphasize because I will say something different later. First Boltzmann-Grad, you get a flight process, then apply diffusive limit to the flight process. As a second step. Then, from these papers of Galavotti and Spohn, we have diffusive limit. For the periodic Lorentz gas, first take the Boltzmann-Grad limit. There are some very deep and beautiful results by Jens Markloff and Andreas Strömbergsson, where they prove that the Boltzmann-Grad limit exists, and they describe the Boltzmann-Grad limit. Then a later paper of myself or Jens Markloff and myself, we do it in any dimension. So we can do it in 2 steps, not 1 step, 2 steps in any dimension for the periodic case, and with super diffusive scale. Mind that this is an important thing, physically different. It goes away fast. Now, interpolating in the random Lorentz gas, this is the random, I didn't try that. The random Lorentz gas, something in between the Holy Grail and what is done here is on the way. We are done, but not yet written down with a PhD student in Bristol. We have a nice result about it. So there are some progress, but we are not yet. Okay. I have 2 more slides, please stay with me for 2 more slides. Another problem is the tagged particle problem. Namely, when you have a gas of particles, that's the original. Because that's I spoke now before in the last 2 slides about the Lorentz gas, when you have fixed scatterers. Now you have a gas of light particles and suspended a heavy one, a bigger one, among them. Assume that the light particles don't interact between them, but they do interact with the huge one. Right? So, and they move according to the laws of physics. These are hard balls, The small hard balls just don't know each other, they go through each other without scattering, it's an idealization. But they interact with the hard ball. Now the motion of the hard ball, again, it has very long memory because it recollides. It can recollide with a particle it's seen already. Say, these two guys now will collide. Now the big one goes away, the small one goes away, but the big one meets some high energy particles and takes over and meets again the previous line. So it can happen. And this causes memory in the program, right? Now we have some results here, and not only me, but it started with Richard Hollis, with Goldstein Leibowitz, myself with Domokos Szász at that time. We had, time is late, so I'm not able to describe now all these results, but for these models, in some limiting procedure, we have results of invariance principle, right? And just to go back, and now I will finish with the last slide. This is my last slide. Going back to Lucretius' curves. Mind that Lucretius' curves was not about, the rational resection said that it was not about small particle colliding, but there is some turbulent motion and follow the trajectory of a particle in turbulent motion. Now a good model of this one is the following. Let V be a vector field be a random vector field, but random. So V is Vx omega. There is a randomness. It's a random vector, which is stationary with respect to translations, ergodic with respect to translations, smooth, assume it's C1 or 2, doesn't matter much. Let's say 2. Twice continuously differentiable. So it's a smooth vector field which is random and stationary body. But the important thing what I assume is that it's divergence free. Almost surely. A divergence free vector field. Divergence free corresponds to incompressibility of the fluid. So that's, and now the classic differential equation I want to understand is dxt is what? You have thermal noise, which is just described by Brownian as in Langevin, as by Langevin, and the force you feel locally is this divergence-free force. Divergence-free. This is the flow lines of the turbulent flow. Can you prove central limit theorem for the long time behavior, long time displacement? It's random walk in random environment. You have a random environment, and you have a diffusion in random environment. You can do the same. You can define a similar thing on the lattice. You will have a random walk in random environment. That's how random walk in random environment problem arose in physics. Because you are mathematicians, you possibly don't know. So the background of random walk, what is a big subject in probability theory, the background is indeed people wanted to understand in the 70s, 80s, this type of thing. Not only this, but the more general, this in particular case. But it comes from there. And again, and the lattice version, I wrote only the SD because that's easier to write on the lattice version. See a number of names here, of course, needless to say that one of them was at the very beginning there, and the problem came from there. And there are many results. So I try to be fair about this. I have 2 recent papers, one with Gatti Cosmo published in the Annals of Probability, and one which is accepted to the Annals of Probability, not yet published, which is about this, on this context, and that's what I will speak about here on Monday and Tuesday. And I hope I will make it a bit longish, but
no, it's perfect.
Okay. So thank you very much for that.
So questions, comments?
Does it get any easier if you, in this last one, if you look at a compact set and look at a periodic field?
Yes.
Would the analysis be any simpler?
No, you mean not compact but periodic?
Periodic.
Infinitely extended but periodic.
Yes.
That's somewhat simple, of course. Okay, then from abstract arguments, if I just say that there is a periodic field which has the properties, then from some very abstract arguments I can conclude the central limit theorem. But if you want more quantitative or limit when the period increases, then it becomes equivalently difficult to dissolve.
Let's thank Bálint for his excellent lecture, and there will be 2 more lectures on, as you just mentioned, on Monday and Tuesday, same time, same place, and he has an office in 3.7.
Yeah,
That's 3rd floor of this building. So if you want to be here,
I'm here all time. So,
so Monday, Tuesday.
Monday, Tuesday.
Yeah. So you can feel free to drop by. Other than a lecture time, you'll be here.
And I'm absolutely happy to discuss mathematics.
Yeah.
And not only mathematics.
So let's thank Bálint once more.